Hey TCMS, this is Mrs. Martin with another day of notes, and today we'll be talking about permutations. And permutations stem directly from the material that we were working on in the previous two videos on Santa Anita. So if you haven't seen those, check those out. They're a good introduction about what we'll be doing today. But before we get into permutations, I want to talk about another bit of mathematics that maybe some of you haven't seen before, and it's this. Okay, now I'm kind of sad because normally in class I would have asked you, what does this math sentence say? And if none of you guys did it, I would have yelled out the number 7 to you. But the exclamation point is not yelling the number 7 at the people who are looking at your work, okay? So we had numbers when we were small, right? As you moved up into middle school and high school, math, we added in letters, and some of you like it and some of you got really upset, like how dare anybody add letters to mathematics. Well, for those of you who are excited about that, then you'll be excited about this. Now we're adding punctuation to mathematics. So there you have it. We had numbers, then there were letters, and now there's punctuation. This might as well be an English class. But all joking aside, this multiplication symbol right here means 7 factorial. Okay, that's what the exclamation point is. It is a symbol representing factorial. All right, and so and actually my printing wasn't the greatest here. Let me make sure everybody sees it. It's almost like factor. That's one word you might see in there, a factor. And when we talk about factors, hopefully it's triggering this idea of multiplication. Okay, so that's going to be important with factorials. And the reason I'm bringing it up, I know it feels kind of random, but we'll need them when we talk about permutations. So factorial has to do with multiplication, and really what this exclamation point means is it's telling us to multiply whole numbers from 7 all the way down to 1. Okay, so 7 factorial can be written as 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, I'm not going to multiply by 0. Why wouldn't that make sense? If you think about it for a second, if I multiply it by 0, then everything factorial is going to be 0, because that 0 would just destroy everything. So we are definitely not multiplying by 0. We stop at 1. Okay, so, and really, I'm sure some people don't even bother with the 1 either. Because if I multiply by 1, it doesn't change anything, right? So some people might not go all the way to 1. I like multiplying all the way down to 1 because when I start doing some canceling in my math, it's nice sometimes to have the placeholder 1, but kind of unnecessary, I suppose. Okay, and so I can multiply these all out using my calculator. Some of your calculators might have the factorial symbol on them, and you can utilize that, but if not, you know what they mean. And when you multiply it out, you get some humongous number. I believe your iPhones have factorial on them. If I check quickly here, they do. So I can type 7 and then hit the X exclamation point, and that does the factorial for me. And that equals 5,040. Okay, so these factorials, they get large pretty quickly. The same way exponents get large pretty quickly. It's all sorts of multiplication happening, so expect big numbers. Some things we might want to keep in mind as we're working through factorials is that all the laws continue to apply as we're working with mathematics, right? So, for example, let me scoot some of this stuff down. If I've got 5 factorial, and I divide that by 3 factorial, okay, I can't simplify here, right? I can't do 5 divided by 3. It's not really what's happening yet. So I'm going to go ahead and set equals, and I'm going to write this out. Okay, there are some rules that you can follow and such, but just for us right now, since we're just starting out, I can just write everything out. So in other words, I'd have 5 times 4 times 3 times 2 times 1. And down here at the bottom, I'd have 3 times 2 times 1, right? So the factorials work counting down, multiplying everything, and we love multiplication because multiplication means that I can just start canceling stuff out, which is always exciting. So I'm gonna go ahead and do that. My 1s can go, my 2s can go, my 3s can go, and all that I've got left over is my 5 and my 4, which means the answer to this problem is 20. Okay, so be on the lookout for factorials as we work through permutations. Another thing we may run into is the following. We might end up with 6 minus 2 and then take factorial of that. So just to make sure everyone's on the same page and nobody tries distributing any factorials or anything like that. Again, just as usual, we're going to start with parentheses, okay? Our order of operations, we're going to start with parentheses. 6 minus 2, that's 4. And then, of course, I can either plug this into my calculator. Again, those of you with an iPhone, if you turn your phone sideways, you do get an X with the factorial symbol. That allows you to do factorials of numbers. Or you can continue practicing with factorials, which I think would be a great idea, and multiply them out, just again to get a sense of how they work, okay? And so I end up with 24. All right, so factorials, we're going to be seeing a lot of them as we work through permutations and combinations, and this is the way they work. So if this is kind of stressing you out, take some time, practice a few practice problems. I will post some in Alex. I'll assign as an assignment. You can see it on the left side down at the bottom. It will come up for homework, so you will get some practice with this. That way, when we get to the word problems, as per usual in our textbook, you're not stumped by the notation. So be ready to practice with the factorial stuff. And again, just remember, you're counting down, you're canceling stuff out, and you're doing a whole lot of multiplication. All right, so one step at a time, but that's factorials. Let's go ahead and move on, and let's start talking permutations, which brings us back to the Santa Anita problem. Okay, so here we go with permutations. In this lesson, we're still going to be utilizing multiplication principle of counting, which we worked with in, not the last few videos because we did the Santa Anita stuff, but the videos prior to that. Except that when we were working with the multiplication principle of counting, we weren't really worried about things happening in order, and we weren't worried about any repetitions occurring because each thing had its own category. So for example, in your homework problem about clothes, you can't wear 2 shirts from the options that you were given, right? So for example, for the uniforms, you wouldn't have worn 2 shirts. So repetition wasn't an issue, you know, we weren't worried about it. Order wasn't an issue. It doesn't matter if I put, you know, my pants first, then my shirt, or my shirt first, then my pants. Although I have heard that some of you have issue with putting one sock, then your shoe, then the other sock, then your shoe, rather than having both your socks, then both your shoes. So I guess for those people, order matters. I've been called a monster for that before. But that's besides the point. Order and repetition did not matter in the last situations when we were trying to figure out how many combinations are possible as we worked through those types of problems where we could write tree diagrams, right? We didn't care about the order things are happening, and we weren't worried about things reoccurring, okay? But now, in the situation at Santa Anita, it was impossible for us to have repetition, right? So for those of you who watched the winners video, we saw that Sharp Samurai came in first. And if Sharp Samurai came in first, it is literally and physically impossible for Sharp Samurai to have taken any other place than that, right? And some of you posted on the discussion and you had, for example, like a typo. Maybe you just weren't, you just missed the fact that you had already written a 2 or something like that, and you wrote 2 twice. And I think that was less of a misunderstanding and more of an oopsie, right? But in that situation, it is impossible for a horse to take 2 places at once. So again, repetition would not be allowed in the permutation situations. Okay, so that's really important, I think, for us to add to our notes here. In other words, we were asking ourselves as we're looking at the scenarios, because it won't always be clear which one you were supposed to use, right? So we have to figure that out on our own. We have to ask ourselves, is repetition allowed? And in the situation with Santa Anita, it was not. It makes no sense. Now, how about order, right? Because order is the other thing that we need to take into consideration now. And when we were talking Santa Anita, order did matter. And even though we did a box trifecta, right? So again, watch the last videos if you don't know what I'm talking about, but if we did a box trifecta, that meant that we would have won no matter what order our 3 favorite horses came in, right? So I guess in some sense we said that order didn't matter, but when we're talking about money, right? If Sharp Samurai came in first, Sharp Samurai's odds were pretty good. If I remember correctly, Sharp Samurai, at the moment that they rang the bell and started the race, the odds for Sharp Samurai to win were 6-5, which is like barely over 1. Okay, so the odds, the fraction was low, which means we were pretty certain that Sharp Samurai would probably take the race, okay, that Sharp Samurai would probably win. However, if the 4th place horse, and I apologize, I can't remember the name of that horse, whose odds were 80-1, if that horse had come in first, the people who had bet money that that horse would win would have gotten a lot of money back. Let me put this into perspective for some of you. If I had bet $1 that that horse would win, I would have gotten $80 back right away. If I would have bet $100 that that horse would win, I would have gotten $8,000 back. So we would have got a lot of money back had we bet on that horse. But the problem is that since the odds were 80-1, everyone was pretty certain that that horse was going to lose. And so nobody's really gambling that kind of money on a horse that they are expecting to lose. So that's a whole lot of talk about horse racing, but all that's just to say that in that situation, order did matter, right? In the words of Ricky Bobby, if you're not first, you're last. So order is important. And as we move forward with this scenario, let's check if order and repetition, how they affect our math. Okay, so let's start with order, okay, since that's the first thing on our list. When we have a scenario, we're going to ask 2 questions. Does order matter? And we're also going to ask ourselves, is repetition allowed? Okay, so let's look at the following scenario. We've got 10 members of the chess club, okay, and they're trying to pick officers from their members. So we need a president, a vice president, a secretary, and a treasurer. So now we have to ask ourselves, does order matter? This is kind of a weird question to ask, does order matter? Because I suppose if I look at this problem, I don't care if I pick vice president first or president first. You know, it feels like, well, not really. It really wouldn't matter if I think of it in that way. But as we're working through permutations, we have to start thinking of it in terms of containers. So let me show you what I mean by containers. So let me scoot this over a little bit. If I had containers, and I had, for example, I've got a container for the president, and I've got a container for the vice president. I've got a spot for the secretary, and I've got a spot for the treasurer. All right, so I've got these positions available or in office for the chess club. So now, does order matter? Well, let's think of it this way. Let's say we've got, we're going to go ahead and put in Sarah, and we'll put in Peter, and we'll put in Caesar, and we'll put in Carla. Okay, so let's say that this was a possible grouping of officers for the chess club after they vote or draw names from a hat, or however they're voting for their officers. Okay, if I switch that order, so instead I put Peter first, and then Sarah, and then Caesar, and then Carla, now I've got to ask you and ask myself, did order matter? Did it matter who I named first? Well, in this situation, our answer would be most definitely yes. Because if I drew Sarah from the hat first, she became president. And then if I picked Peter, he would have become vice president, and so on and so forth. If I had switched that and instead pulled Peter out of the hat first, he became president. And then Sarah vice president, and so on and so forth. So when we're thinking about does order matter, we have to think about not necessarily how these positions would have been picked in real life, but more about if I had positions set, does swapping around names on those positions change the outcome? Okay. When we were doing things like the yogurt problem before, it didn't matter if I put, think about what you're doing in your yogurt cup, right? If I put my yogurt first and then my toppings, that's one way of doing it. If I put my toppings first, and I don't know if any of you do that, that seems kind of strange, but if you put your toppings first and then the yogurt on top, you're still eating the same stuff. That wouldn't have changed what ended up in your yogurt cup. It wouldn't have changed what you paid for when you went to go and weigh your yogurt cup and pay for that. So in those past problems that we've been doing, order did not matter. Okay, but now with Sarah, Peter, Caesar, Carla, in this situation of picking officers, it does matter who's first and second because it's determining which position they take. Okay, so does order matter? Yes, it does. Now let's consider the situation of repetition. I think this one is a little easier to answer. Can anybody take two positions? And the answer would be no, generally. I know in my past club experience, there were some times where, maybe one person was secretary and treasurer at the same time, but for the sake of our problem, we're going to assume that there's, since there's 10 members of the club, there's plenty of people to choose from in order to take each individual office position. Okay, so does order matter? Yes. Is repetition allowed? No. And so we can determine that this is a permutation. Okay, we're going to be using the work that we learned for permutations because order matters and repetition is not allowed. Okay, so let's consider now the possibilities. Okay. First, we're going to start with the president. Okay, let's say when we meet with our chess club, we decide, all right, guys, we're going to put names in a hat. That's how we're deciding on the positions this year because everybody's equally excellent at chess club right now, and nobody can really decide on who's the best to be president. So we're just going to play it fair, and we're going to draw names out of a hat. All right, so in this first box, and I'll go ahead and use green here. In this first box, we've got all members available. Okay, all the names are in the hat, and I could potentially pick any member at the beginning to be president, right? So if we have 10 members, that means we've got 10 options for president. Now let's think about the vice president. Now let's consider this first scenario, right? If I took this first name and I got Sarah, right? I'm not going to put Sarah's name back into the hat. That makes no sense. And Sarah could possibly get picked for a VP, secretary, and treasurer. So we leave Sarah out of it. And so now how many options are left? Well, if you think about it carefully, with Sarah out of the game, we've only got 9 options left. Okay, and then we think about the secretary. So now we've got the president taken care of. The vice president has now been assigned. And how many people are left to possibly be assigned as secretary? If you're thinking 8, you've got the right answer. And then for treasurer, you probably get the pattern by now. We've got 7 different possibilities for treasurer. Now, what about the rest of the members, right? The other 6 people left over. Well, the other 6 people who are left over, we're not worried about. They didn't take office this year. It was the luck of the draw because we're just drawing from a hat. So now we've got all these numbers, and you might be wondering, what do we do with them? This is where our multiplication principle of counting comes in. Because again, we are multiplying the options for each category. Same way we multiplied options for the clothes and for the ice cream and in the birthday problem, for those of you who are in period 1, we're multiplying because these are the options in each category. Okay, so I'm going to go ahead and multiply these guys. So to recap, the president, we had 10 options because we had the opportunity to pick from all 10 members. Once we pick the president, this box ends up only with 9 because it's all members minus, maybe I should write the word minus the president. Okay, president has been chosen. Once we get to secretary, we've got all members minus the president and the vice president, and so on and so forth. We're just subtracting the people who have already received a position. Okay, and now we can multiply them because they all represented options for a certain category, which is what we did in the previous material. So now that I've got 10, 9, 8, 7, I can go ahead and set an answer for myself by using a calculator probably. And I get 5,040. Okay, so 5,040 is the possible combinations that could be made, or the possible, let me not use the word combination because we're doing permutations right now. 5,040 are the possible groupings that could occur when I'm trying to find out officers from a chess club. Okay, now that seems a little stressful if you ask me. I mean, you only had 4 people to pick, and you're only picking 4 people out of a group of 10. And thank goodness we didn't have to write this out as a list, because had we had to write this out as a list, we would have been here for quite a while writing 5,040 different possibilities of officers for the chess club. So again, and I'm going to scoot this over a bit so we can focus just on the numbers. This 5,040 represents the number of possible groupings of 4 chess officers out of 10 members. Okay, so and we're not doing what we did with just 4 people swapping them around, because you have the option of 10 different members to pick from, not just the 4, like when you picked winners for Santa Anita. So lots of different possibilities. So if we're getting numbers like 5,000 and we're only picking 4 out of a group of 10, when we start working with problems with larger numbers, these numbers are going to get pretty large pretty quickly. And I don't want you to have to sit there and spend time making huge lists. So we need to find some way of taking care of this using some math, some computation here. So hopefully you're seeing 10, 9, 8, 7, and something in your brain is triggering the stuff that we did at the beginning of this video, which is factorials. Okay, hopefully you're seeing that. So let's do that. Okay, so let's use factorials to take care of this problem. So 10987, that makes me think of 10 factorial, right? And what's 10 factorial? If I think about it carefully, I know it's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But that's a problem. Because what did we need to figure out president, vice president, secretary, and treasurer? We needed only 10, 9, 8, and 7. Gosh, now we have 6, 5, 4, 3, 2, 1 left over, which is kind of troublesome. Wouldn't it be nice if we could use some math to get rid of that extra stuff? Well, lucky for us, there is some extra math I can do. And you know this math. You've known this math since Algebra 1, right? If I want to get rid of something and it's being multiplied, I'm going to use my division property of equality to cancel it out, right? Those are our inverse properties. We learned those at the beginning of Algebra 1, and gosh, wasn't that a long time ago? So I can go ahead and get rid of 6, 5, 4, 3, 2, and 1 by just dividing it on both sides. But you know what? I'm going to be very math savvy, and instead of writing 6, 5, 4, 3, 2, 1 over here on the left side, I'm just going to write 6 factorial. These mean the same thing, right? So if they mean the same thing, I'm allowed to divide them on both sides. I haven't broken any math rules. As a matter of fact, I followed them very carefully. And now I can cancel out 6, 5, 4, 3, 2, and 1, which was our goal, right? Because now we've got that leftover, we've got that 5,040. Okay, so let's take a look at this work just for a minute and label some things here. Where does 10 come from? And forget the math that we did before as far as filling in the boxes. Where is 10 in our original situation? Hopefully, 10 is triggering in your memory that this was the number of members to choose from, right? This is how many we had to pick from for officers. Okay, but what about 6? I mean, 6 wasn't anywhere in the word problem. If I read it back again, there are 10 members in the chess club. We are picking president, vice president, secretary, and treasurer. Nowhere in that word problem was there a 6. But I did mention 6 when we were talking about our work from before. If I've got 10, 9, 8, 7 as my options for president, vice president, secretary, and treasurer, how many members are left over to just be regular members? If you're saying 6 out loud, because I know you guys are answering my questions out loud at home, 6 is right there, the leftover. Okay, that sounds kind of mean, but I don't mean that in a negative way. I just mean the people who did not get chosen for office. Okay, so let's not say leftover. That sounds so mean. People not chosen for office. And remember, this was random, so no hurt feelings, right? You just picked them at random from the hat. Okay, so now we're kind of coming up with a sort of pattern here for problems where where order matters and we don't have repetition. Okay, so when order matters, as it did in this situation, okay, when order matters, we call these things permutations. And permutations have a special notation, which you'll probably see not only in your textbook, but also in your ALEX program, and also as you move forward in math. It uses the letter P. And let me try and color code this here. So P for permutation. We've got a letter N. We've got a letter K. Okay, and when I talk about this, this means N choose K. When I read that out loud, you know, that type of math notation, I'm saying N choose K. So let me go ahead and scoot this over now that we know where the permutation stuff comes from. So we've got permutation N choose K, where N represents the total group. Okay, in the chess club problem, we were talking about 10 people. And K is going to represent the number of people, or I guess sometimes it could be things, that are chosen. Okay, so out of N, we're choosing K. Out of 10 members of the chess club, we chose 4. Okay, and then our formula ends up looking something like this. We've got N factorial. We don't have a letter for leftovers. We only had a letter for how many we had and then how many we took from there. But if you listen to yourself say that, right, how many I had and then how many I took away, that equals the leftovers, right? This is like elementary school thinking about subtraction, take away. So if I'm taking things away from N and I need the leftover, so again, let's say that out loud. I'm taking away from N. K is how many I'm taking away from N, and then this represents my leftovers, right? That's what we were talking about before. We didn't like the word leftovers before, but we'll use it for now just to save us some time. So we've got the total group. We've got the leftovers, and we've got the factorials happening to take care of those. All right, so thinking back to the chess club example, which we wrote out before, or a minute ago, we wrote out all the work, trying to think critically about how those things are happening, where those numbers are coming from, not just blindly memorizing equations. Now I've got, in the chess club example, I've got a permutation, again, because order matters. We've got a permutation where we had a group of 10, and from that group of 10, we selected 4 officers. And that's going to look like this. We've got the 10 members divided by the 10 members minus the ones that I selected from there. And we started this whole lesson off with factorials, right? And we talked about parentheses already, so you've got that down. Now we can go ahead and write 10 factorial divided by our leftovers, 6 factorial, which is what we had already figured out when we worked out the chess club example very carefully together. Okay, where I can plug those into a calculator very carefully. Or I can multiply it out and cancel some numbers first, so that I get 10 times 9 times 8 times 7, which results in 5,040. So there's quite a bit of math going on in this one with permutations. I feel that the letters are pretty straightforward, but it can get kind of tricky when you have very wordy word problems. where it's kind of hard to determine how many there are, what are you choosing, does order matter, you know, and so on and so forth. So what I'm going to do for you guys for this topic, because I do believe that it requires some practice with the formula and with the notation and all that sort of thing. I will be assigning you a permutations practice. It will be assigned in Alex, so it won't be coming directly from your textbook yet, because I want to make sure, again, that you guys can practice with the formula before we jump into difficult problems from the textbook. So when you go into your Alex, just like normal, on the left side where you usually see your time and topic goal, you will see an assignment called permutation practice. Okay, there'll be a couple of problems on there for you to do. I plan to make the assignment unlimited attempts, okay, because it is not my intention for you to try one time, and if you don't get it, then too bad, so sad, right? It's never been like that, even when we were back in school in person. So if you do the assignment and you get 3 out of 5, for example, go back. I'll make sure it's set to do a quick retake, which means you only have to redo the problems that you got incorrect. Okay, so if you get anything incorrect, go back, do those again, and they'll add to your overall score. And my hope and dream is that I can look on Alex and see that everybody got 100%. Okay, so please make sure that after you watch this video, and hopefully you took notes during this, you collect your notes at your side, and you go to Alex and you do the permutation practice. It will be your classwork / homework assignment for today. All right, and again, as always, feel free to message me. Many of my TCMS students, I'm happy to say, have been messaging me with questions, like direct questions for clarification on the homework or clarification on the videos or notes, and I love it because that means you guys are doing the assignments and you're watching the videos, and it helps me get better at explaining things to you guys. So again, if you have questions or comments, make sure you message me so that I can make any clarification that you need, or in the next video, I can add some of those questions that you guys are stuck on. Okay, so as always, as I'm signing off, I'd like to thank you all for always watching my videos, for trying your best to complete everything that you need to complete, for completing, you know, fulfilling your responsibilities. I'm really happy to continue working with you with the time that we have left in the semester, and I hope to hear from all of you soon. Take care.